There we go. We fired up the recording. And I want to put on record the offer that I sent out email. I will, as far as grade enhancement activities, what I will do, and I've done this in the past, and it really worked out pretty well, I thought. I mean, I think there's some logic to it even. If you make a higher grade on the final exam than you do on either one of the semester tests, I will replace the lower of your semester grades with the final grade. So that final grade could count for your final exam and one of your other two tests. And I do that for a couple of reasons. One, it really keeps you interested in studying for the final, that's for sure. Especially if you've and it lets you have one bad day on a test. That as long as you do well on the final, it's completely wiped out. You know, so I think that's a pretty fair offer, and the material builds on itself, and so to do really well on the final, you're going to have to be pretty conversant in the whole course. I don't go back and necessarily give chapter 3 problems, but as you go through this, everything kind of builds on itself. And so if you can be successful at the end of the course on the final, that means that you have probably pretty well mastered or have a pretty good working knowledge of the material. So at any rate, the grades were in general quite good. I emailed out the grades. They were shuffled in all kinds of crazy order, so you don't know who made what. You can probably identify your score on there, but in general, they were quite good. There's a few that need to be better, and so those folks can take advantage of this offer. But if you did not do well on the first one, then you really are kind of under the gun on the second one and the final. And there's no enhancement to the final. The final is whatever comes back out of iLearn. Okay, so I've tried to figure out a good way to go through this. So what I'm going to do is I'm just going to do a preview of the exam. And this thing comes out in all different orders. It shuffles them all over the place. So I don't know the order, but we'll just go through them. If it's a problem, I have worked it out and I have a written solution that I will show you. So question number 1, the study of classical thermodynamics takes which point of view? Well, it's not microscopic for sure. It's not mesoscopic, so it pretty well has to be macroscopic, unless, you know, you could say none of these, but that's not correct, and it's sure not all of them, so it's this guy.
And it kind of makes sense classical, they didn't really have the ability to go microscopic.
Well, that's right. That's right. There weren't great microscopes back in those days, and, you know, so anyway. Okay. A closed system refers to a fixed quantity of mass. That's just, you know, our definition. So those are pretty straightforward. Okay, so this is the polytropic gas question. Gas undergoes a polytropic process from 1 bar pressure and 1.2 cubic meters volume to a final pressure of 10 bar and a final volume of 0.3 meters cubed. What is the exponent n in the equation for the polytropic process? Described by pressure times total volume raised to the n power equals to a constant. Okay, so let me pull up my written solutions here, if I can find it. It's this yellow page over here. And I didn't know what order these are coming up in, so we just have to go by and find. There's the polytropic process. Okay, so a little bit of a restatement of the problem. So you see state 1 and state 2. So since the equation says these two are equal to each other, get this out of here, at any state along the way, so then we can write P1, V1 to the n is equal to P2, V2 to the n is equal to P3, V3 to the n, however many state points that we have. We only have 2, so we write that. And then you can go ahead and plug numbers in if you want to, or you can go ahead and solve it in a equation form and then plug in at the end. I went ahead and stuck the numbers in. So that says 1 bar times 1.2 meters cubed raised to the n power is equal to 10 bars times 0.3 meters cubed raised to the n power. So I've divided through by 10. So I get 1/10 over on this side, and it disappears on this side. And then I divided through by the 1.2 meters cubed to the n. So it groups up over here on the right. And then I take the log of both sides of this. So I get the log of 0.1 is equal to n, the law of exponents and logs and all that good stuff, times the log of 0.25. And so you can punch these on your calculator. So you simply solve for n and you get 1.661. So that's the answer to this guy, 1.661. Okay. Question 4. A rigid tank contains 10,000 kilograms of water at 300 degrees C and 10 megapascals. What's the volume of the tank? Okay. Roll back to the solution. Let's see. Where's there we go. So, what's the volume of the tank? Well, we want to check for the saturation conditions. All right. And so, let's see, we're given 10 megapascals, but before you can go in the tables, you know, you got to convert to bar. And so 10 MPa is 100 bar. And we're 300 degrees C, so let's run into the tables real quick. Roughly. Atmospheric pressure in bar is 1.014. So it's close, but it's not exact. All right, now let's see. I think it's this one that I want. Okay.
So you can, if you just want to get a general idea, you can wing it.
That's true. I mean, it's not going to be very far off. Okay. So what did we say? We said 100 bar and 300. So let's see. Here's 100 bar. And we see that the saturation temperature is 311.1. Well, we're at 300. Well, so, I mean, we're trying to identify the state that this water is in. Well, for it to be saturated at 100 bar, it has to be 311.1 degrees. If it's hotter than that, it's going to be superheated vapor. And if it's cooler than that, it's going to be subcooled or compressed liquid. So this is subcooled or compressed liquid, okay? So we can pop back to, not this one, too many files to juggle. Okay, so, I mean, what we need is the specific volume. And so we've got a compressed liquid. It's not very far into compressed liquid. It's pretty close to saturation. So the rule of thumb is that if we're compressed liquid and we want specific volume, we go look at the temperature. These properties are strongly a function of temperature and weakly a function of pressure. So what we want to do is we want to go to the saturation temperature table at 300 and pull the specific volume. And we can look at it at the saturation pressure and just see, you could probably get the same answer by, you know, when selecting if you pulled either one of them, but the correct one to go to is the temperature table at 300. Okay, so let's go back over here. And just note, this is 100 bar, and that number is 0.00145. Okay, let's go back to the, let's see, this is temperature. So I want 300 on this table. So here is 0.00140. So it's about 0.05 difference. Or, well, no, it's not. It's 0.05 times 10 to the minus third difference.
Aren't they above the pressure, though?
I'm sorry, what?
Is that the critical pressure next to 300 to 85.81?
The critical pressure is right here.
Yeah. Oh, okay. But the pressure we're at is above that, so it would be.
We're at 100.
You say it would be slightly compressed, then, right?
I can't hear you.
The liquid is slightly compressed?
Yes.
Okay.
I'm sorry, I just can't hear. Oh, okay, okay. Okay, so this is the specific volume we want, 0.00140036. So because we know we're compressed liquid, and we are going to the temperature table because these properties are strongly a function of temperature. So with that, let's see. Okay, so this is the number out of the table for specific volume, 0.00140036, and multiply that. And of course, that's meters cubed per kilogram. And so we know we have 10,000 kilograms. So I multiply those two together. Kilograms goes out, and I get 14.036 meters cubed. And then I can hop back to the test. And so that is 14. All right, so on to number 5. And this is probably the best or the most involved, probably the most difficult question on the test. Water is boiled in a pan on a stove at sea level. During 15 minutes of boiling, it's observed that 150 grams of water, or 0.15 kilograms, has evaporated. Calculate the heat transfer rate. All right, well, let's go. That's all the way down here at the end. I think that's the last one I did here. Is it? No, not quite. No. Sorry. There we go. Okay. There we go. So the writing just restates the question. So I drew a little picture here. So you can think about that. It's a constant pressure process, right? Because this is boiling in the atmosphere. So we can think about the old piston. The frictionless piston cylinder is our constant pressure container for a control mass. So you can think about this as having a piston cylinder that maintains a pressure inside the container on the liquid or the vapor or the mixture of 1.014 bar, because that's atmospheric pressure. And we can see that in the tables. If you go out to 100 degrees C, you look at the saturation pressure, and that's the saturation pressure. So that has to be atmospheric pressure, standard atmosphere. So we've got 0.15 kilograms, saturated liquid water, because this is an ongoing boiling process. So the water is already boiling when we start thinking about this 0.15 being evaporated from it. So we know we have saturated liquid, and we want to know how much heat did we have to put in, or actually the rate. We're going to turn it into a rate, but first of all, I calculated the amount. And so to go from this state 1 to this state 2, which is just boiling this off to saturated vapor, okay? So it's the same pressure. And so, and it's going to be a lot larger volume, because that specific volume really changes from liquid to vapor. Okay, so if I write the first law, I started out writing E2, total energy at 2 minus total energy at 1, but you're going to throw out kinetic potential energy of the whole container. And so that's going to reduce to internal energy at 2 minus internal energy at 1 is equal to the heat that was added minus the work that was done. Okay, well, this is constant pressure work, right? Because this piston gets raised. So that's this gas or this substance doing work on the surroundings, because it pushes it back up. Okay, so, and I know constant pressure work is P delta V, so it's that constant pressure times V2 minus V1. So that's what the first law says. Okay, so these E's turned into cap U's, and then I can also write that as the mass times the specific internal energy, U2 minus U1 is equal to Q minus M times pressure times the specific volume change. So this is just transferring from total volume to specific volume. If I do that, I got to put the mass out front to multiply through. Okay? Well, then let's rearrange this. And so Q then is equal to, put all this other stuff on the other side of the equation. I get this, and then I rearrange it a little bit. And you know what? U2 plus P specific volume 2 is the enthalpy at 2. So you don't have to do this, but if you realize that, that all of this condenses into just the enthalpy difference, I mean, this problem really just falls apart. But it takes some insight and some juggling of those terms to see it. Now, you don't have to do this. You can go ahead and work it from this basis, and you'll get the same answer. It's just a little quicker and easier if you see that. So realizing that then, this is at, it's happening at 100 degrees C. So let me go to my tables. Let's see, this is temperature. Okay, so here's 100 degrees C. There's that saturation pressure, atmospheric pressure. And over here, this is enthalpy of the liquid, enthalpy of the vapor, and my goodness, they've even subtracted it for me. So this minus this is 2257, and that's the number I need. So I don't even have to do any subtraction. I can just pull 2257 directly out of this table and plug it into my solution, which is what I've done. Okay, so the heat that had the heat transfer, the heat that had to be added to vaporize that is the 2257. That's per kilogram, but I only did 0.15 kilograms. So that's 338.55 kilojoules. Because the units on this are kilojoules per kilogram. And then, but it wants the rate per minute. Well, this occurred over 15 minutes. So I just divide it by 15 and I get 22.57, which got rounded to 22.6 on the answer sheet. And so right here, bingo, is the answer to this question. Okay, pressure is an example of an intensive property. If you have a container that's at a constant pressure, if you cut it, the container size in half, you still have the same pressure. So that's a characteristic of an intensive. It's not mass dependent. It's not like energy or something. So that's intensive. Okay. The reciprocal of specific volume is density, 1 over. What specific volume is what? Meters cubed per kilogram, and density is kilograms per meters cubed. So just 1 over. Okay, so a rigid tank contains 7 kilograms of an ideal gas. So we can use the ideal gas law at a pressure of 500 kPa and 30 degrees C. A valve is opened and half the mass of gas is allowed to escape from the tank. The new pressure in the tank, after that we've cut the amount of mass in half, is 150 kPa. I want you to find the final temperature. All right. So here we go. I don't know where it is. Here it is. All right. It's right down here at the bottom. Okay. So what we can do is we can write the ideal gas law for state 1 and state 2, and then we can ratio them, is the easiest way to think about this. So I start out and I write P1 V1 is equal to M1 R gas constant T1, and I can divide it, you know, so long as you divide by the same thing on both sides, you can divide by anything. Well, I'm going to divide by the ideal gas law written at state 2. So, and since P2 V2 is equal to M2 R T2, then I can divide, I'm going to divide on this side in terms of pressure and volume, and this side in terms of mass, gas constant, and temperature. But these two are equal, so, I mean, it doesn't make any difference. It's the same number. So then when I do that, I realize, well, this is a rigid tank, and the tank volume's not changing, so the V's cancel. V1's equal to V2, and it drops out. Well, I know the relationship, M1 is 2 times M2, but they don't drop out. The gas constant is the same, and the temperature is not the same, okay? So canceling the gas constant and the volume, I get this relation, and then I just plug numbers in. So the initial pressure is 500, the final pressure is 150. I've got 7 kilograms. It gets cut in half, so it's 3.5. Remember, I've got to use Kelvin in the ideal gas law. Don't be sticking degree C in here. You'd be getting wrong numbers. So what is that? 303 degrees K and divided by T2. So simple expression, just solve for T2. It comes out 181.8 K. And this is probably the most confusing part, is turning that back into C.
Oh my God, I'm an idiot.
So you know that what the conversion is degree C plus 273, and that has to equal degree K, which is 181.8. So when you solve it, you get minus 91.2 degrees C. So minus 91 C. Okay. I kind of went crazy on this electrical stuff here. I don't think I realized I was putting so much kW on there. I guess I'm a wannabe electrical engineer or something. You know, I don't know. But anyway, it's all good. It's all good. Okay, so we've got a 1.5 kW electric resistance heater, which I have in my office downstairs. Because my office every morning when I come in is 65.4 degrees. It's a daggum meat locker in there, you know? So I've told them they won't fix it. So I turn on my little chill chaser, and after about 3 hours, it warms up.
3 hours.
Yeah, that's a little bit of an exaggeration, but it takes at least an hour, hour and a half to bring it up a couple of degrees. Okay, anyway.
Like right at your leg. I know, because I've got a room in my house that's like that.
Okay, 1.5 kW electric resistance heater in a room is turned on for 20 minutes. The amount of energy transferred from the heater to the room is, okay, so let's go to solution 1.5 water. There we go. Okay, and I didn't draw a control volume. So there's two ways to look at this. If your control mass is just the air, then it's a heat transfer term and there's no work. If the heater is included inside your control mass chamber and electricity passes in through the boundary, then it's work. But either way, you're going to get the same number. I mean, it doesn't matter. So it's still the same energy coming in. So just a kW is a kilojoule a second, just what it is. A watt is a joule a second, and a joule is what? A Newton meter per second. I can't tell you how much I hate these units, but anyway, every time I teach thermo, I get pretty good at them again, and then I don't teach thermo in a while, and I try my best to forget them, but they come back.
But it's satisfying when you run an equation and all the units cancel to the thing.
Exactly. I mean, half of getting right numbers is just being able to get the units right. So anyway, this is 1.5 kilojoules per second. Well, how many seconds did it run? It ran for, what is that? That's 1,200 seconds times 1.5. You could do this math in your head, is 1,800 kilojoules. So this one's pretty straightforward. So it should be 1,800. Bingo. Okay. A quantity is a property if and only if Its change in value between two states is independent of process. That's just our definition of a property. It doesn't matter how you get there. Now, for work and heat transfer and all that, it matters how you get there, so they're not properties. So this one is just definitional. Bingo.
Some form of energy is a property too. Internal energy? Is internal energy a property?
Yes.
Okay.
Yes. Okay. Question 11. Heat transfer to a system during a process is positive, right? If it's added, it's positive. If it's lost, it's negative in terms of heat transfer. According to our sign convention, work done on a control mass by the surroundings is negative. Because that brings energy in. We got a minus sign in the first law, then those two minus signs counteract to turn to a positive, which makes the energy go up. But the definition of the work itself is negative in this situation. So it's a negative quantity. Okay, some more calculations. 230 meters, a 230 meter cube rigid tank is filled with a saturated liquid vapor mixture of water at 120 degrees C. If 25% of the mass is liquid, 75% of the mass is vapor, determine the total mass in the tank. Okay, well, it's saturated, so you know all you got to do is go to the saturation temperature table, and you can find the pressure. Of course, I didn't ask you that, but you know, it's true. Okay, let's see how much. There we go. Okay, so I guess the first thing I did is I went ahead and went to the table. I mean, it's pretty obvious you're going to need these specific volumes. So we're 120 degrees C. So let's go check these specific volumes in the table. Let's see. So 120, we're right here. And of course, this is, you got to move the decimal point, 0.0010603 and 0.8919. So let's blitz back real quick. I keep messing that up. Okay, and those are the correct numbers for specific volume, and those are both meters cubed per kilogram. Okay, so I just say, well, let's let X equal the total mass. Okay, well then, if X is the total mass, then how much mass of liquid do we have? Well, 0.25, because 25% of it is liquid. How much vapor do I have in the mass state, or in the vapor state? 0.75x. So, golly, let me just write a little equation here. So the total volume of the tank has to be the volume, or the mass of the liquid, which is 0.25x, times the specific volume, which is 0.0010603, plus the amount of vapor, the mass of vapor, 0.75x, times the specific volume of the vapor, 0.8919. So I just do, you know, my algebra is not real good, but by golly, I can handle that one. So you get 343.7 out of that. And so it rounds to 344. So bingo, right there. Okay. Another problem, determine the amount of power transmitted into a control mass by a paddle wheel that mixes the fluid inside. The shaft turning the mixing wheel rotates at 300 RPM, that's revolutions per minute, and transmit 500 Newton meters of torque.
That conversion took me forever to figure out. I convert from RPM to radian per second.
I know. You learned it so far back in high school that you forgot it.
I'm not even sure we ever learned.
Well, you may not have. But anyway, I think I saw that. I see that guy up here. Yeah, here we go. Yeah, I know. So the equation, the power, the rate of doing work, is the torque times the angular velocity, and that has to be the torques in Newton meters and, or the rotational speed, I guess, in radians per second, okay? Well, so that's the big question is, can you convert? Do you know that there's 2 pi radians in 360 degrees? You know, all this stuff, you know, they pounded you in physics, I'm sure. They probably pounded you in dynamics with this a little bit. Yeah, but anyway, so 300 revolutions per minute times 2 pi radians per revolution divided by 60 seconds per minute. And so your omega is 31 point, it's like pi with the decimal point moved one place is the way it comes out. 31.4159 radians per second. Multiply that by the torque, which is 500 Newton meters. And so we get 15,708 really Newton meters per second. And a Newton meter per second is a joule per second. So that's the same thing as watts per second, or I mean watts, but you got to divide by 1,000 to get to kW. Because, you know, I'm trying to scramble the units on you a little bit. Sorry. It's just what professors do. So, which one? It was this one, wasn't it? I almost forgot the number. Okay.
Is it going to grade your test that you're doing right now?
Do what now?
Is it going to grade this for you?
Oh, yeah, yeah. But, okay, so I'll tell a story on myself. When I came in here a little early, and I thought, you know, I hope I really know all the answers to these, at least what I put, you know, because when you put the questions in, you got to put the right answer. So I went through the test and clicked all the answers that I had before anybody got here to make sure it gave me 100, because I thought it's going to be really embarrassing if I don't make 100 on this. But I did. Thank heavens. But I did think about that. I said, ooh, that's going to be bad. Okay, let's see. So this is, we got another rigid tank. With it's 0.2 meters cubed, 8 kilograms of water at 500 kPa. We just want to know the temperature in the tank. So this is just playing in the tables a little bit. There we go. No, number 2 on this list. Okay, so I don't think we need to read it again. So, well, the first thing you got to figure out 500 kPa in bars, which is 5 bar. And then you want to go look up the specific volume of the liquid and the vapor to see what those are. We'll go check those in a minute. But since this is your pressure, if your specific volume for that container is between these two, then you've got some sort of a 2-phase mixture. And it doesn't ask you to determine the quality or anything. But so you know total volume and you know total mass. So you know total specific volume, which is 0.025. And you say, well, 0.025 is bigger than this. So that's on the liquid side of the dome. And then this is on the gas side of the dome, which is 0.37. That's 0.37 is way bigger than this. So this number is in between these two. So I have to be at the saturation temperature at 5 bar, okay? So we can try to look at those numbers and we'll verify those when we go to the table here. So let's see, I'm 5. I want to go to the pressure table at 5 bar. There you go. There's 5 bar. This is, yeah, pressure. And so that's the saturated liquid, 0.0010926. And that's for the liquid, and the vapor is 0.3749. And 0.025 is certainly in between those. And so I've got to be 151.9 because I'm inside the dome. Okay? So let's go back. So 151.9 rounds to 152, and we're off and rolling. Okay, a single phase electric resistance heater is operating in a factory. The voltage is 480. The current is measured at 22.5. How much heat is input to the factory from the heater in 1 hour of operation? Now, just a comment on the side, if this was three-phase, we'd have to multiply by the square root of 3. And if it was going to an induction motor or something, there's a factor called a power factor that's in there, which is less than 1. A number like 0.8, 0.85, which would go in there. But we're not doing electrical engineering stuff in here, so all that gets glossed over. But calculating electrical power from measured data is not quite as simple in general as this would indicate.
This would also, this would be assuming 100% efficiency, right?
Well, yes.
Work.
Yeah, that's right. And so if you were wanting to calculate shaft work on a motor, the amount of power going out, if you measure the electricity in, that motor is probably 95% efficient. So 5% of the power that you measure does not get converted into torque.
Right.
That's absolutely correct.
And the same thing is true here, right? Because some of that power could be released in light, sound.
Not much.
Not much?
Not much. A strip heater is pretty much, it's like 99 point something. I mean, it's pretty darn close. Because all that electricity does is flow through that. There's a little bit of resistance before it gets to that heating coil, but that heating coil resistance is huge, and the resistance of those wires is tiny. And so, it's like 99+% gets converted into heat. That's why in thermal we always do electric resistance heaters, because it kind of makes it not so bad on some of the assumptions that you're glossing over. Okay, so let's see. This is the okay. Here we go. So this one's pretty simple. So kW, volts times amps, is watts divided by 1,000 is kW. So it's 10.8 kW, and kW is a kilojoule a second. And then multiply it by, it's an hour. So there's 60 times 60 is 3,600 seconds per hour, 38,800 kilojoules. So that's this guy. Okay, adiabatic process is one for which there is no heat transfer. Process is considered to be quasi-equilibrium process, so that which of the following will be defined for the entire process? It's the properties. Because, it's like the example of a non-equilibrium or a non-quasi-equilibrium process is like an explosion in the cylinder on your car. When that thing fires off, there is a process that goes on. It is so chaotic and so rapid that you just can't write an equation that relates all of the properties. It's too chaotic. So when we start studying thermo, we want to use the ideal gas law. We want to integrate some of these relations. And in order to do that, that relates like a polytropic process, where you've got pressure and volume related through an exponent. Well, but if the process is so chaotic that that relationship doesn't hold, then when you integrate that relationship over the process, you get garbage. So the only way that you can make that halfway valid is to make some sort of an assumption like this, where we go very slowly. We take one grain of sand at a time off of the top of the piston, and we let the pressure we let it move as the pressure, you know, changes. You know, the force is down is less, so the thing moves up. And, you know, so something like that could take a month to actually do. But so that's kind of the concept behind the quasi-static or quasi-equilibrium process. It's so those properties stay in that mathematical relationship to each other as you go from state 1 to state 2. So its properties. Okay, water at 60 bar and 250 C is, all right, let's see, let's go to our property. So what is it, 60 bar and 260. So 60 bar, well, to be saturated, it has to be 275.6. It's only 260. It's too cold. So it's subcooled / compressed liquid. You can do it there. Or let's see, what did we say? We said it's 260. So we can also go 260 in the tables. And so the saturation pressure is 46 and we're 60. So the pressure is too high for it to be saturated. So it's compressed there. You can tell by going to whichever table that you like. You can tell I kind of like going to the pressure table and looking at temperature, but you can do it either way. Okay, so that's compressed liquid, and one more. Oh yes, nitrogen gas. At a temperature of 127 Kelvin, pretty chilly, and 35 bar, pretty high pressure, can be considered an ideal gas. And that's the question, yes, no, or some of this garbage, some of these garbage answers. So, well, I mean, what's our only, to determine whether a gas can be treated as an ideal gas, we only have one tool. We have one tool. It's the generalized compressibility factor chart. That's all we got, okay, at this point. So that's what you got to do. You got to use that chart. All right, so that's number 1 up here. Okay, so, well, you got to go look up the critical temperature and the critical pressure. Well, how do you do that? You got to go to the right table. It's this. No. You got to go to 2 tables in this one. It's this one up at the top. There we go. So we've got the 3rd column is critical temperature, and the 4th column is critical pressure. And so nitrogen, critical temperature is 126, and critical pressure is 33.9. And that's degrees K and bar. And then, let's see, we need to go back to this guy. So we got those. And so you get the, what is relative? There's relative and reduced. I always get them confused. Anyway, you take your temperature and divide it by TC. This is reduced, I believe. And so that number is basically 1.008. And the reduced pressure is your pressure divided by critical, 1.032. So they're basically almost 1, both of them. And then let's see, we have to go to the compressibility factor chart. There's a couple of them here. This one shows it pretty good. So here's the reduced pressure, which is 1. And here's your reduced temperature. There's 1. So they're real close. So you're where this meets this. So you're someplace right over in here for your Z factor, which is about 0.3. Well, you can only assume ideal gas if you're someplace up here in the neighborhood of, 0.95 to 1. So you're nowhere close. I mean, so this problem was built to give you a really low Z factor. So you would say, no, it's not an ideal gas. So it's not an ideal gas. The answer is no.
Also, just realizing that nitrogen nitrogen, that full, but that compressed, probably not gas.
Those molecules, I'm not sure. I mean, well, I know, but nitrogen, liquid nitrogen is very cold. So, I mean, I don't know. You'd have to research. I don't know off the top of my head. Okay, so let's submit the quiz. Allow to be graded in the quiz grade area. Oh, I don't care. So anyway, I think I got them all right. We'll go down the bottom. 42 of 42, thank heavens. Okay, so that's quiz 1. I would expect the same general format on quiz 2 and the final. Lots of little, fairly short problems. Now, what's going to happen is the number of problems will probably go down because the problems get a little more complex as we go forward. So whereas you had 20 questions, I don't know, roughly half or something, maybe a little more, was calculations. I would just expect maybe 15 or so on the next one. We'll see. I'll give you guidance. I don't have it made up yet, but basically it'll be very similar in nature to this. Okay? All right, let's see. How we doing time on this? So 9:30, 10:30. Yeah, okay. So we still have some time. So we're going to hop into chapter 4. And I've been making slides like crazy. And I don't have all of them made that I'm going to make because honestly, some of these PowerPoints they provide are pretty pitiful. They don't really put very much of the chapter in there. And I mean, for this type of teaching where we're recording, I pretty much have to use something I can get on the screen. So one way or the other, I'm going to cover all of the material in here that I think is important, whether I have to enhance the slides or whether we just look at some stuff directly out of the textbook. But we're going to talk through all of this stuff. Okay, so chapter 4, it's really starting to get good now. Controlled volume analysis using energy. So now we get to some more fun devices. We get to pumps and turbines and compressors and, you know, some more real world type stuff that people actually use a lot of in there. We're not limited to piston cylinders and electrical work across a boundary and stuff like that. Okay, learning outcomes. I'm not gonna, y'all can look at these. This is what you're supposed to learn. I hope you do. Okay, so about this first 7 or 8 slides I put in last night and this morning. So we're going to go through the development of a mass balance for a controlled volume. And we're going to start out with a controlled mass, and then we're going to do some very simple mathematics. And I like to do this because, especially on the mass balance, because it's very simple. I mean, you're going to feel like that I'm just belaboring the obvious, but it's good to really understand this process because with energy, you get a lot more terms. When you get to your fluid mechanics, if you're taking fluids, you have to derive all of the big equations. And oh my goodness, you use this same kind of approach, but there's so many terms. And it's so easy to get confused and lost, especially in your fluids courses, that getting a good foundation in doing these balances and deriving equations from them, I think is really will help you for your entire engineering career. Even if you're doing solid mechanics, you know, they start with these little elements and they push on the top and they push on the bottom and they do that in fluids and you get a shear stress and all this sort of thing. So, you know, starting with a simple little model and then developing like the Navier-Stokes equations is pretty amazing when you really think about it. Okay, so we're going to start with a controlled mass. Okay, so which is a fixed quantity of mass that occupies different regions at time t, and then later, a delta t later. So we got 2 times. The starting time is t, the ending time is t plus delta t. And so at time t, the mass is contained in region I, this little region, in the pipe. And of course, that's going to flow in as we go through this delta T. But all of our mass, some of it is in that pipe poised to come in, and the rest of it is in the control volume. And you see the dashed line around this little circular, looks kind of like a kidney or a liver or something. I don't know what it is. But that's the control volume. So this region MI, or region I, is outside the control volume, okay? But we're going to consider that mass, okay? And then the control volume is the circular region. And there's nothing over here in the exit pipe at time T, okay? But then we take another snapshot of delta T later, and what's happened? Well, the mass that was in region I has now entered the control volume, and so it's now within that boundary. And it's possible that boundary got bigger or smaller. I mean, this could be like a balloon. You could be, you could not have an exit, and you could be blowing up a balloon, in which case the balloon gets bigger and bigger until it has a catastrophic event. And then the problem's over, I guess. Exactly. You just woke up the cat, I mean, I don't know. Then at time T plus delta T, then we still have mass in the control volume, plus now we have some mass that has flowed into the exit pipe, and that's region E for exit. And so, but if you add up the mass in the control volume and the mass at E, it equals the mass at time T that was in I plus the control volume. So we don't have any leaks in the system. Okay, so what happens during the time interval? And like I said, this is going to be belaboring the obvious pretty quick. The mass in region I flows into the control volume. The mass in region E flows out of the control volume. And the masses within regions, that should be little I, doggone it, screwed that up, and E, as well as the control volume, differ between times T and T plus delta T, but the total mass under consideration remains constant. So yeah, region I goes from having mass to having nothing. Region E goes from having nothing to having mass. And if those two aren't equal, then we could have increased the mass in the control volume, or we could have decreased the mass in the control volume, just depending on how big the mass in I is and the mass in E is. Okay, so now let's start putting some math to this. So mathematically, we can see that the mass in the control volume at time T plus M sub I equals the mass in the control volume at T plus delta T plus M sub E. So I believe I got that typed correctly. Or just rearranging, we just pull the control volume terms to one side and put the entering and leaving terms on the other side. So the mass in the control volume at T plus delta T minus the mass in the control volume at T is equal to the mass that entered, M sub I, minus the mass that left, M sub E. Yeah, pretty simple stuff. Oh, sure. Now, I have emailed this out to you, but I mean, it's good to take notes too. That's fine. Okay. Everybody good? Just slow me down. I get on a roll and like a freight train rolling down a hill, I got to put my brake on every once in a while. All right. So this last equation we can think of as an accounting balance for mass. We're like bean counters or something. It states that the change in mass of the control volume during the time interval delta T depends on the amount of mass that enters less the amount of mass that exits. Duh, how many times are you going to say that? And the answer is a few more. Putting the equation on a time rate basis, oh yes, yields. Okay, so, you know, as we like to do in calculus, we're going to what? Divide by delta T, and then we're going to take the limit as delta T approaches 0. So that's just the previous equation, all the terms divided by delta T, which is some fairly large. It could be somewhat small time interval, but we're going to shrink it. Okay, in the limit as delta T goes to 0, we yield or get this. So we get dmCV dt is equal to now m dot entering and m dot exiting. And it is possible to have more than one pipe coming in, and it's possible to have more than one pipe going out, whatever. And so if you have more than one, that becomes a summation, as we'll see. I didn't think to do it on the equations I wrote, but the author provides that here in just a minute. But so it can be a summation. This right now looks like it's just for one inlet pipe and one exit pipe, but you can have more of each. The time rate of change of mass within the control volume is equal to the rate at which mass enters the control volume minus the rate at which mass leaves the control volume. Okay. All right, that's the end of the stuff I added. Then we've got some that your author has put in here. Okay, so this is where he starts. So he's just showing a control volume up there, and he just writes the word. He doesn't go through all those details, which I don't like, because I think it's instrumental to make sure you know where all this stuff comes from. But anyway, just in words, you know, we've already said all of this multiple times. Time rate of change of mass contained within the control volume at time t is equal to the time rate of flow of mass in across the inlet I at time t minus the time rate of flow of mass out across exit E at time t. And so then he just writes the equation. So that's what we already had. Okay, in practice, there may be several locations on the boundary through which mass enters and exits. Multiple inlets and exits are accounted for by introducing summations. So we just put a summation. And so if you've got 3 inlets, you have to sum what's coming in over 3 inlets. If you got 10 inlets here, that summation then would go from 1 to 10. Same thing on exits. You could have 10 inlets and 10 small inlets and 1 big exit, you know, just whatever. It depends on what the device is. Okay, so this is the mass rate balance for control volumes with several inlets and exits. Okay, let's see. Steady state. Okay, steady state. So when we start working problems, he'll a lot of times they'll say assume steady state conditions, and so we got to be sure that we understand exactly what that means. Well, steady state means all properties are unchanging with time. Okay, so nothing varies with time. Well, so if you look at this equation back here, we've got dmCV dt. And if that's not varying with time, guess what? That puppy gets set equal to 0. And that's what he's saying right there. And so if that's 0, then we just pull the exits to the other side of the equation. So both terms are positive, and bingo, we get this. Okay? So steady state, yeah, that says that whatever's coming in has to be equal to whatever's going out. or we would be building mass or losing mass in the control volume. So we got a big tank, we're flowing, you know, hot water in, we got, you know, maybe it's a big tank, it stratifies and we pull cool water out the bottom, but the tank level stays the same. So whatever's coming in equals whatever's going out. Okay, now there's also a discussion of one-dimensional flow. And there's a bunch of assumptions associated with this. So one is that the flow is normal to the boundary at locations where mass enters and exits the control volume. Now, I mean, in a general real world situation, I mean, you got water flowing in through a pipe. I mean, that stuff's twisting, turning, turbulent flow, chaotic. I mean, it's, you know, in general, it has a bulk velocity moving this way. But if you get down right on that boundary, you've got all kinds of velocity vectors, okay? But, you know, you worry about that in fluids. We ain't doing that here. So we make this one-dimensional flow assumption, which we make, I mean, just about for everything in here. And that means that when you get a velocity, it's normal perpendicular to the plane, the area that mass is passing through as it comes into the control line. Or where it's exiting, it's normal to it. All intensive properties are uniform with position, so they over each inlet or exit area through which matter flows. Now, it is possible to have a distribution along that area, but it doesn't change with position. So at each point on that area, all your intensive properties are uniform. It doesn't say that you can't have a variation across that inlet. It just says that whatever it is, it's constant with position. And we see he's got a little example of an air compressor. So, you know, and that dashed line is his control volume, you know, which cuts through the pipes and it cuts through the cord. So, right, so we've got a work term and we've got air entering and exiting. And there's heat loss from the motor and the air compressor. So there's probably some heat transfer coming out across that boundary as well, but he's not doing the energy balance yet. So we're not going to talk about that. Okay, so this is important. So, you know, make sure that you're comfortable with this. So the mass flow rate, we can calculate as A, that cross-sectional area. So that's what? That's meters squared or feet squared. And that's velocity, that's average velocity, normal velocity across that area. So that's feet, you can do feet or meters, doesn't matter. I'll do feet on this one. So area is feet squared, velocity is feet per second. So AV is a volume flow rate. Cubic feet per second, cubic feet per minute, you know, whatever your time base is on velocity, probably second. Or it could be meters cubed per second, okay? Well, that's volume, but this is an M dot. And so to get from that volume flow to a mass flow, we've got to use either density or specific volume. They're 1 over, it doesn't matter. So if we divide by specific volume, that's what feet cubed per pound mass or feet cubed per, or meters cubed per kilogram. So that converts that volume flow into a mass flow. So you'll see that as cap A area. When you see that, those units need to come to mind. A area square somethings, V velocity, feet per second, meter per second, some length per second. When you multiply them together, you get a volume flow, cubic meters per second, cubic feet per second. And when I divide by specific volume, I get rid of the cubic feet or cubic meters and I introduce mass. So it's the specific volume. So you could equally write that, and a lot of books do, and your book does too, as rho, which is density, rho AV. It's the same thing. Because multiplying by rho is the same thing as dividing by V. 6 of one, a half dozen of the other. You know, do you want to multiply by 0.1 or do you want to divide by 10? It's the same thing. I mean, you know, just, you know, do you want to draw the line and not, you know? This gets used. And, you know, if you're asked to calculate velocity, if you're asked to calculate areas, like in pipes that are flow through, that sort of thing, you have to go back to this. You know, so this gets used, this gets thrown in as you know, you'll be working a problem A, B, C, D, E. Well, E will be, well, you know, you got a mass flow rate that says, well, if the velocity can't be more than, you know, 100 feet per second, what should the cross-sectional area of the pipe be? Well, this is where you go to solve for area or velocity a lot of times if you have mass flow. Or if you have a volume flow, you got to hit a mass flow, you wind up going here. So this gets used a lot. Okay, so how are we doing time-wise? So I don't want to blitz through to the energy balance yet, but I don't want to also waste time. So what I have done, so, and I apologize for not getting this into the slides. I did the best that I could, and I did not get, so this is just your textbook. So I scanned part of it, and you can see where he has made his slides. You know, that's the word definition of the mass rate balance. But there's some stuff in here. This is what I cut and pasted that figure, and then I went through all of this discussion, putting on all these equations because I think it's important. Here's the figure where he develops this relationship for the normal velocity and the cross-sectional area. So he draws this thing and he shows this little cylinder, but it's kind of skewed off at the side, and it has this velocity vector that's not normal. Okay, this is kind of the more general condition. He says, well, okay, but for this one-dimensional flow, what we're going to do is we're going to talk about this normal component, which is perpendicular to this area. And I'm going to say that the volume that we get in this normal velocity times this area is the same volume as this kind of tilting cylinder that is the actual mass that's flowing in. So it just kind of shows that approximation. And you can read through here. I'm not going to just read all this stuff out of the textbook to you. But so now he's doing some math on this, which we've kind of done, but now he's using density instead of specific volume. So, you know, like I said, you can divide by density, you can multiply, or you can divide by specific volume, you multiply by density. So here he's multiplying by density. So, you know, this is, this combination provides an amount of mass. And I think it's instrumental to look at units on this, right? So I've got a dA over here. So that's going to be like square feet, right? I've got a velocity, so that's going to be feet per second, okay? And so if I multiply those two together, I know I get cubic feet per second. If I multiply by that by density, I get pound mass per second, right? Because the density takes out the cubic foot and, you know, replaces it with pound mass per second. And this is the number of seconds. So when you multiply all this together, you get an amount of mass that is crossing through this sectional area. I really encourage you to write out units on these things, because you see these things, when you see the relationship, if you don't write out the units, you can't really see, you can't see the magic in the equation. You know, the units will show you what's going on. So I was sitting there looking at that. Now, you know, he says that's mass. Is that really mass? You know, well, he's got area, velocity, time, density, you know. So I just took a piece of paper and I just said, okay, velocity, feet per second. Area, feet squared. Multiply those together, cubic feet per second. Times density, pounds mass per second. Times delta T, 10 seconds. Oh yeah, that is a mass, you know. And once you do that a couple times, then you start to really understand the equation. It's not just, you know, an equation. It's something that you own and can work with. You know, you do enough of this and you just say, I don't need that. I'll just make up my own equation because I know what's going on. And I really want you to get to that point. Okay. So then he's going to divide by, let's see, dividing both sides of the equation by delta T. Well, it's going to come out on this side. And taking the limit, then this becomes a flow rate. And yeah, you know, if I take the delta T out of here, then, you know, this is going to be per second or for whatever my time base is, right? Because I've got time in the velocity, that's feet per second, and I got nothing to take it out. So this is going to be, you know, mass flow per second or per time base. And so this is instantaneous rate of mass. So all of a sudden now, okay, I can agree with that. Okay, but here's what I want to get to, and I'm going to run out of there. So now, we'll also have an integral formulation of these things. In more complicated problems, you have to use the integral formulation. Because look at this. This says that mass flow rate across a boundary. So we're integrating across an area. So we're integrating all around this dA up here. And what are we integrating? Well, we have a density function. And remember, density can change with position. Now, Lord, I'd hate to be the one that has to come up with the density function of position, but if you had one, and you know, we could make up a simple one or something, and people out there doing experimental work, maybe they take data and curve fit one. I mean, I don't know. But this density, this is a function of position, and this is this normal velocity, which I guess can also be a function of position, but we almost always assume it's just constant, but it could be. And then this is dA. So then we're integrating all over this area that has this mass coming in. And so, but this shows you how you could put into an analysis the variation in density with position on that area that the fluid is coming in or exiting. You say you just have to you have to have an equation to put in there that you can integrate over this area. And then you just integrate, you know, all over the area at which it's coming in, you know, a little dA at a time. Okay? That makes sense? Okay. All right. Y'all got that look. The look. Teachers know the look, you know. We might keep talking, but it's over once you start getting the look, and I'm getting the look. So, okay. So I will shut up. I will post this, and I sent you homework problems, so start looking at them. I'll send you solutions. This is Thursday, so we're a little out of our normal sync. I'll send them to you probably tomorrow to go ahead and try to get you back on sync. And you know, again, these are not terrible, so you didn't get quite 15, but it's hard to pull back, much as I try. So y'all have a great weekend, and I will see you on Tuesday.